Okay, let's look at inductors in chapter 33.8. So inductors store energy in the magnetic field. And we can look at how this works. So let's say we have a circuit with a switch as shown below. So for example, we have a switch this way, and then this circuit has a battery and then a resistor. So if we turn the switch, so this is a switch S. So when the switch is closed, what we have is something like this, where the current goes this way and that way, and this is your EMF. Sorry, this is EMF and that's EMF. So there is what we can have is the EMF induced in the coil. So we can say that when the current or when the switch is closed, so the current flows in the coil. And we can say that the current produces a magnetic field. So we can say the increasing flux produces an EMF. So the increasing flux creates an EMF in the circuit. And we can say this induced EMF is in a direction that will induce a current. And so this is the current I, and then we're going to have a loop like that, okay, a magnetic field that way. Okay, so the induced EMF is in direction as to induce a current in the loop that will oppose the current flowing. So we can say that the direction of the induced EMF is opposite the direction of the EMF of the battery. The induced EMF is called a back EMF. Okay, the induced EMF is called a back EMF because of its direction. So this effect is called self-inductance, and we can say the EMF E subscript L is called self-induced EMF. So we can define the self-induced EMF next. So the self-induced EMF is proportional to the rate of change of current. So we can say that for a loop of wire, we'll say that E subscript L is equal to minus L di dt, where L is the inductance of the loop. So we can say inductance L depends on the geometry of the loop. So we can say that if we have a loop of n turns, then we can say the inductance L is equal to n phi subscript b over over I, where phi subscript b is the magnetic flux. So this is magnetic flux. So L is a scalar quantity, and it's measured in henries. The symbol will be H. Let's see, I think we're going to use lowercase h on this. Let me make sure. No, actually it's fine, uppercase H. So the symbol is henries. So 1 Henry is equal to, actually, let me make sure my spelling is not correct. This is the name of a person, so I didn't do it right. This is henries, or in Henry H. Inductance is measured in Henry H. Okay, so 1 Henry is equal to 1 H, and that's equal to 1 Weber per ampere, or you can write 1 Tesla meter squared per ampere. And so let's do an example where we use something like this. So let's consider the case of a solenoid. And so in this case, let's see, so the magnetic flux phi subscript b would be equal to BA, which we can write as mu naught n I times A, where the magnetic field of the solenoid is given by that quantity mu naught Ni, if you remember. Okay, and so the flux or the inductance L can be written as, so we know L is equal to n phi subscript b over I, so we shall just write it as n times mu naught And in this case, we have mu naught n A over L, where we are saying that the lowercase n is equal to uppercase n over L. So lowercase n is the number density, which is the number of turns per unit length. Okay, so L can be written as mu naught n squared A over L. Okay, mu naught n squared A over L, where A is the area of a cross section, n is number of turns, and L is the length of the solenoid. So this formula is the inductance of a solenoid of length L with n turns. Okay. So if we have a toroid, we'll do something similar. So you just need to know the magnetic field of a toroid, and then we can calculate the flux for the toroid and plug that all in to get the inductance of a toroid. So L is the inductance.
So the inductance of solenoid with R.
What did you say?
Can you repeat that again, please? That's the formula for the.
So this is the inductance of a solenoid of length L and number of turns n, and A is the cross-sectional area of the face through which the magnetic field goes through. So, for example, let me see if I can find an example to draw for you. So, for example, you have a solenoid like this, and we are saying that the current is going in this way, and so if the current is going in that way, and the field this way, okay, and then it comes out on this end. So this is the magnetic field B. So we are saying that this is the length L, and this has n turns, and the face through which the magnetic field is going is the area A, the cross-sectional area A. And so it would have, for example, a potential difference across the end, like that. And this is the delta VL, potential difference across the inductor. Oh, sorry, hold on a second. We'll say delta VL, delta VL for the inductor is the same as the EMF L, or EMF subscript L, which we said was equal to minus L di dt, or in some books you will say the EMF is given by absolute value L di dt. So you can use the absolute value also the same way. Let me write it nicer. So this is L, and this is absolute value, okay? Questions on this at this point? Okay, let's look at the energy stored in the inductor next. So we can say how much energy is stored in an inductor, because we started off by saying that the inductor is a device for storing energy in a magnetic field. So let's look at how much energy is stored in the inductor. Okay. So we start off by saying that the power dissipated is given by power equals current times delta V L. So the power dissipated, we know by definition, is current times voltage. So in the inductor, it's going to be delta V subscript L. That will be the power in the inductor. Okay. And we know that, so P in the inductor is equal to I times E subscript L, or the EMF in the inductor. So we can say this is I, and then we have minus L di dt for the inductor that way. So the power in the inductor is going to be equal to minus Li di dt, where we can replace power in order to find energy. We know power is the energy per unit time, or the rate at which work is done. So it's energy per unit time. So this is the energy used in the inductor per unit time. So from there, let's go here. So we can say that the power usage in the inductor is given by du, which is energy used in the inductor with respect to time, and that's equal to minus L di dt, minus Li di dt.
Is that power equals d mu or dV?
Power is current times voltage, and I'm just saying the voltage is delta V subscript L. Are you talking of up there?
The P, yeah, I got it.
Yeah, delta V is a potential drop across the inductor. Let me make sure that I'm getting the energy use. And let me see. So the energy is being transferred. So the energy is being lost. Okay, so this is the energy in the inductor. So the energy in the inductor P subscript L is going to be this energy. This is positive. So this is the electrical energy used. So the energy being lost to the inductor is minus Li di dt, and the energy in the inductor is P subscript L, which is du subscript L dt, which is a positive L di dt. Because the energy is being lost to the inductor, so the inductor is gaining the energy, so the energy coming in the inductor is positive. Okay, so du the L, or du subscript L, can be written as L subscript I, or Li di that way. So I'm just removing the dt's, and then we can say u subscript L is the integral of Li di, like that. So u subscript L, energy in the inductor is given by, energy stored in the inductor is Li over 2 squared, okay, or half Li squared. You see it commonly written that way. This is the energy stored in the inductor. Okay. Let's look at what it would be for a solenoid. So suppose we want to see energy stored, or we want the energy stored in a solenoid. So we shall use u subscript L equals half Li squared, and then we'll just take the L for a solenoid. The L for a solenoid was given by, what was L for a solenoid? We found that to be equal to mu naught n squared A over L. So this was what we found for the inductance of a solenoid. So the energy stored in the solenoid U subscript L is given by half mu naught n squared A, and I have I squared, and you can put the L here. So this will be the energy stored in the solenoid. And we can do a few more things, but I think we can leave it at this point now, this way. Questions on where we are now? So what we've seen is we've shown that we can find the self-inductance of a coil, the induced EMF of a coil, E subscript L, which is minus L di dt. We define inductance as L equals the number of turns, the flux divided by the current, and then we use that to find the inductance of a solenoid. And we also found the energy stored in the solenoid, which is what we've shown right now. So we can leave this alone and go to the next section if there are no questions on it. Okay. One thing we might do, maybe we just do a small example before we go on. So let's use this formula in an example. This example is out of your textbook. This is example 33.14 in textbook. Okay, so here the example says that the 10 microhenry, so a 10 microhenry inductor. So let's do it this way: a 10 microhenry inductor is 5.7 centimeters long and 4 millimeters in diameter. And we can say, suppose it carries a 100 milliamp current. So we say what the energy stored and the field strength. So we're looking for energy stored and the field strength. And also the energy density. Let me add energy density to it. So the magnetic field strength and the energy density. Okay. So let me see. So energy density is energy per unit volume. So it's the energy stored per unit volume. Okay, so you're going to have energy stored is U subscript L over volume of the solenoid. And so once you get an energy density, then you can find a magnetic field. B is going to be equal to, let's see, the energy density. So B is given by square root of 2, and then you have energy density. Energy density is given as U subscript B. So it's going to be U subscript B times mu naught. Okay, so this is, I'm just giving you the formulas that you need to do this exercise. So you already know UL, so you should be able to complete the exercise. When you are doing solenoid volume, use cross-sectional area times length. So pi r squared L, cross-sectional area times length. Mu naught is 1.26 times 10 to negative 6 Tesla meters per ampere. So mu naught. So what do we have for energy stored in the inductance, or energy stored in the inductor? So who has an answer for that? Did you convert? Did you guys?
I did.
Okay.
Well,
So this should be in the unit of joules. Okay, so let's look at it here then. You said L is 10 microhenries, right?
Yeah.
So 10 to the negative 6.
That's where I screwed up.
Okay.
I did -9.
Okay. So then we can take 3 off of that. It's micro. So 10 micro, no, it will be, if it's 10 to negative 6 instead of 9, then it's 8. We're just taking 3 off of it. Instead of negative 11, we should have negative 8, because instead of negative 9, we should have negative 6. That's what I'm saying. So L should be 10 microhenries, and then current I is 100 milliamperes, so times 10 to negative 3.
So that's milli.
Yes, milli.
Micro as well.
Let me see. I thought I wrote M. Let me see. How do I? Maybe I should find a better way of writing it. But you see, the M is different from the micro.
Okay.
Yeah.
Okay, never mind. Yeah, my mistake too.
Yeah. So it's pretty straightforward. If you know the formula, you just plug it in, as you can see. So it's going to be half times 10. Yeah, negative 6, and then you have 100 times 10 to negative 3 squared, like that. Okay. So this should give you 5 times 10 to negative 8 joules. And then the energy density, UB, this is now UB, is energy U subscript L over volume, which is going to be U subscript L over pi r squared times L for the volume of the solenoid. Okay. So volume is given by pi r squared L, where L is the length of the solenoid. So we have 3 times 10, 3.142. So by the way, did anyone get an answer for volume, or did anyone calculate that separately?
I got 1.7.
10 to negative 2.
Yeah.
That should be cubic meters, hopefully. So you should have volume should be 3.142. What is the radius? The diameter is 4.
The radius is 2.
Yeah.
Oh.
So you should have 2 times 10 to negative 3 squared,
Yeah,
and then times 5.7 centimeters, so it's 0.057 meters. Like that.
2.28 times 10 to the negative 7 times pi. I didn't multiply the pi ends.
Oh, okay. Yeah, let's multiply it through. What do you say?
That's 7.1 times 10 to the negative 7.
Okay, we'll see. Yeah, 7. That is the correct end. 7.1 or 7.2. Okay.
7.166.
So this is cubic meters. So this one is not the right answer. Okay. So now energy density is given by, what is our value for energy density then? It's going to be U subscript L over volume. So all you do is divide your energy by the volume. So what do you have for that?
7 times 10 to the negative 6.
Okay. 7 times 10 to negative 2.
Yeah, this is 6.98, but if you round that up, it's going to be 7.
Okay. Joules per cubic meter. That's good. And then from that, we can find the magnetic field strength B. So B is the square root of 2 energy density times mu naught. Okay. So calculate the magnetic field and tell me what you have. Say it again.
4.2 times 10 to the negative 4.
So Tesla, 4.2 times 10 to negative 4. That will be correct. That's what I have here. Very good. So I think we've calculated the entire thing that we need to calculate, so I think we are good.